Hi, Christian.
Hello.
Welcome to the podcast Everyday Metallurgy.
Thank you. And
Today we're going to hear about something very exotic. Uh, Many people don't know how to make diamonds. But if they want to make diamonds, they should get your number after this episode, I'm sure. Because we are going to learn something about how to make the most advanced tools for shape forming of hard formable metals and even some of the most extreme materials where the forces are on Superman level. Uh, Christian, can you give a short introduction to who you are and the company you work for?
sure. And thank you for the introduction. I'll say my name is Christian Jepsen, and I wish you welcome here to Strecon this afternoon. Here at Strecon, we have the tagline, building strength by stripwinding. And building strength for what? And one of the applications is actually making high strength tooling for the diamond synthetic diamond industry, but we also do many other things than that. Actually, I would like to give you an introduction to the different applications we are into, so you have idea what we are building strength for. And mostly is actually for forming different kind of metals. So I actually lined up the different applications fields. And so I would like to start in what I would call the low pressure area, below 1000 megapascal. And here I can show you, and here I can show you it's aluminum yoke. It is actually for the steering connection in a car. And as I said, that is forming that from a cold brick of aluminum. There you are below 1000 megapascal. And actually, we do not need the strength of our tooling for that. It is actually more because of the stiffness, because we can also pre-stress carbide, cemented carbide, and there we gain is stiffness, and that's actually more for that application. Then we have the, I'll say, main application, and that is in the pressure range of 1500 megapascal, and that is actually the cold forming of steel. And here I can show you here one example that is it's a bevel gear sitting in the differential of a car, and here you see the die for it.
Yeah.
And out here to the very right, I have some of the high pressure applications Peter mentioned in the introduction.
Yeah.
And here you will actually see a piece of carbon with embedded diamonds, very small diamonds.
What size are they?
They're actually comparable with sugar. They're sugar in size. I can also show you some CBN grains. I don't know if you can.
Yeah.
It's more like sugar. There are thousands of CBN grains in here, and they are produced for cutting, for different cutting applications in the steel industry. But here we are actually in the pressure range exceeding 5000 megapascal. In order to actually grow crystals, diamond structures, crystals, there you have to exceed 5500 megapascal, and you also have to obtain a temperature between 1200 and 1400 Celsius C. And there, if you have semen of a diamond and you have carbon, then you can start to grow a crystal from there. And I have to say, we are not making the diamonds. We are making some of the tooling for it.
Yeah.
I actually have a son at home. At the age of 8, he was asking me, "You are making tooling for diamond, and then you sell it."
Yeah.
We're not actually making diamonds, but we make the tooling for it.
Yeah, but it's like making the press for money. The guy who makes the press must be the rich guy.
Yes, but there are so many things into it actually to make to have the full process of making these diamonds, and I think everyone have to actually to focus on this the focus area, and what we are focused on is actually the whole pre-stressing thing, because what is common for these applications is that you need very hard dies in order to cope with the pressure. So if you take that as an example for the bevel gear, where you are actually a co-forming steel with the pressure of 1,500 megapascal, you need a very hard die, and hard dies, they are brittle.
Yes.
So they can very well cope with pressure, but if you go into tensile stresses, that they will break immediately. And therefore you have to compress them. You have to put them into compression, and therefore you have to put them into a compression ring. That's just to say what the basic idea is.
Yeah.
Here I've actually brought a compression ring, and you will see. Then you can actually put the die here inside, and then the conical shaped, and then you can actually, with the press fit, then you can pre-stress the die by pressing it into the compression ring. Then you have the interference. Of course, the die is bigger than the hole in the compression ring. And we've actually done that, I would say, for ages. I would say for 80, 100 years back, it is a well-known technology of doing so. But the thing was, going up in pressure, going up in hardness of the compression rings, then back in the 50s, 60s, and 70s, you actually see a lot of accidents where these compression rings, they started to explode. You had a fragile breakage of these compression rings. And then my predecessor, Jens Grønbæk, he started back in the 70s, also more than 50, that would actually be 50 years back. He started to actually to look into, not to make a strong compression ring, but actually to make a safe one, a safe ring that will break in a controlled way.
Yeah.
And there he started to look into, could you actually do that with multiple layers of strip? And the idea of making reinforcement by winding with strip and wire is actually not new. And you've known that for more than 100 years. In the beginning, they actually start to reinforce the barrels of cannons by winding. So that's actually known for many years. But
to avoid fatigue or to avoid cracking, or what was the reason for that?
Actually, to be honest, back 100 years back, the casting process was very unsafe. So I actually think it was just a measure to try to reduce the risk, and it was based on trial and error. But what Jens Grønbæk did 50 years back was actually try to analyze what is actually happening, and then he started actually to make experiments by what happens if you take a core. Here has actually, maybe I should say, a strip-winded compression ring exists of three major things. You have an inner ring we call a winding core. Then you have a strip area, and then you have a casing. Here's an example of a winding core, and here's the strip. And as you see, I almost believe you can hear it's very flexible.
Yes.
But nevertheless, it is Rockwell 64 hard and has a yield point exceeding 2,000 megapascal. It is just because it's so thin. It's 1/10 of a millimeter thick.
Yeah.
And that's you can.
Is it just plain carbon steel, or what is it made of?
It is actually a high alloy steel, and then it is the strength is by cold rolling. It is enhance the strength of the strip.
Yeah.
And the idea is that you then start to wind around an inner core. And then layer by layer you will introduce compression. And the way of actually get an idea of what's happening, I think if you that's actually a rubber band I have cut in two. And if you want to have an idea of what actually happened, and then try to wind that around your finger. The first revolution, you will think nothing happens, but if you actually do it 10 times,
it will cut your finger off.
Yeah, it's actually starting to cut your finger off.
Yeah.
And that is actually the idea of making a strip-on container, that you layer by layer you can build up strength. And I would actually like to show you some also theoretical background around what happens actually with the stresses in a strip-on container, and why we in that process can enhance the strength so much, because it's not just because of the material data of the strip. And therefore I'll try to show a little bit about the stress distribution in a conventional ring, and what we actually can have in a strip-on container.
I'm also curious. So the material itself, if you take a hard metal, how high can you go in strength before that breaks? Is that 3,000, 3,500 megapascal?
Yeah, I would say the strip we have, we never exceed, whatever we do, we never exceed the yield point of the material we uses. Because that would lead to a plastic deformation of the compression ring. So we always in the elastic area, because that way you can reuse the containers and they're stable over time.
Yeah.
But with a strip like the one I'm showing here, it's as thin as paper. It has the width of 100 millimeters, and you can actually lift a car in it without going into yield.
Okay.
With a yield point of 2,000 megapascal, and here we actually have 10 square millimeters. It's the 100 times 0.1. That was you can actually load that with 2 tons, and it's still elastic, full elastic.
Okay.
And if you then start to add one revolution after in pre-stressing, then you can actually obtain an insane level of pre-stressing. I can try to come with some examples with the big containers we are making.
Yeah. Hey, while Christian is finding his slides he would like to show, I'll just interrupt and try to relate this hardness he's talking about, because he said 64 Rockwell C. Is that hard? If we compare, a tooth has a hardness around 25 Rockwell C. It's pretty hard. A stone, typical stone you find at the beach or in your garden, has a hardness of around 51. And if we relate to one of my last episodes on Damascus steel, the sword material, that is the winner, the toughest, the hardest steel you could make in weapon industry for many years. The hardness of a Damascus steel varies between 59 and 67. So 64, it's absolutely on the max level of what you can get out of material. So what Christian's working on, it's very hard.
Here I'll show you just what happens. I told you the example. If you just have a single ring, you are loading when you use a single ring for pre-stressing. And out here on the left, just to give some background, there we have this gray area that is the die that is loaded with the inner pressure, and that is put into a compression ring, a single ring compression, in this light blue color out here. And what happens is when you load it with the inner pressure, then it will start to expand. And due to geometry, give this. That is. if you load that, if you load the die on the inside with the inner pressure, then the whole assembly will start to expand, and the expansion is actually leading to that you start to get tangential tensile stresses. So it's actually the radial inner pressure is expanding the die is expanding the compression ring, so you're actually getting to a bigger diameter, and then you start to get tensile stresses. But due to geometry and the law of physics, then you will actually on the inside of the compression ring, you will have very high tangential stresses. Yes, they're shown here by this red curve.
Yeah.
You can see on the inside they're very high, but due to geometry, going to the outside, they actually are fading out to almost nothing. And therefore, you do not have actually good usage of your ring. It is highly overloaded on the inside, and it's doing nothing on the outside. So all the money you have invested in the most expensive tool still you can have, it is doing nothing on the outside. And it will come to a yield point when the equivalent stress, the combination of the radial and the tangential stresses, when they exceed the yield point, that's shown up here. This dotted line is actually showing the yield yield limitation, and you will see you will reach that on the inside of compression far before it is doing anything on the outside. And that is really a huge limitation to a single ring compression ring. Then you can actually divide your compression ring up into two rings. Then you actually just have half the problem. Because then you can also put outer pressure to the inner ring. But nevertheless, you will always have that every time you have a ring with a certain thickness, and you load that radial, then it has very high stresses on the inside and doing nothing on the outside. And when I then here in the next example, I'll show what actually happens in a strip-wound container. Again, we have here the inside, that is the die. Then you have this more dark gray area, and that is the ring. That is actually the ring we are winding this strip material onto. And there we can actually manipulate with the stresses for every single revolution. And then we have some out-clever mathematics, how to actually to find out how to control these stresses during the winding. And then we actually have a model where we can predict what under load, what is the geometry of the compression ring, and how should we then design the stress distribution during winding that under full load in a compression ring, the stresses are the same all the way out. And here you can see we have a lot of rings. For every 10th millimeter, we have a ring, and it still have the same behavior. That is bigger on the inside than the outside, but it's actually like nothing because it is only over 1/10 of a millimeter. And that way, we actually can have that the equivalent stress all the way from the inside to the outside is the same. And I'll say that is the biggest thing. It is even bigger than we have this really strong material. That is actually that we use every single fiber in our compression ring to build strength. And when we look into our company name, Strecon, then it is actually meaning constant stress. And that is actually referring to here that we can have constant equivalent stresses throughout the complete ring.
So the inner ring is preloaded in compaction when you start.
When we start, I have to say then this inner ring is not even there. It is during the manufacturing. This is the die. That is actually what our customer is loading. And therefore we also have to find a way to predict what the stresses will be with that thing pressed into and with the inner load. But due to calculations, we can actually calculate backwards and then say we need that specific stress distribution that we have constant stress under load.
Yeah.
And I think we will go back to my table here, because then I can show. We'll do like this. Give me a second. Yes. And
yeah.
And that is actually the idea for building big and for building small stripward containers. And actually, what you see here, that is some of the smallest. That's the smaller container we're making with the outer diameter of 35 millimeters. And you can see it still have a winding core. It has a strip area, and it has a casing.
Yeah.
And that we also do up to the diameter of 2 meters. The biggest we are making, we have ever made was 2 meters, and we actually make quite a few, about 1,200 to 1,500 millimeters, and those are used for this diamond industry manufacturing.
Yeah.
And these big size, that will actually give you an idea of actually the level of pre-stressing. Because if we make a container that is 1.4 meters, then the winding core, the inner diameter of the winding core is 500 millimeters. And will have a thickness of 50 millimeters. So you have to imagine that ring of a hardened steel ring. And then during to this strip winding process I have shown you, we will reduce the inner diameter with 5 millimeters.
Oh.
And you can actually almost see it with your bare eye.
Yeah.
So you actually are building a ring with the inner diameter of 500 millimeter, the outer diameter of 1,300, 400 millimeters. And that inner ring is reduced with 5 millimeters and have a conical shape, about 1 degree. And then you can take a solid piece of carbide with the outer diameter of 505 millimeters. So the piece you're pressing in is 5 millimeters bigger than the hole.
Yeah.
And that's actually give you an idea of the level of pre-stressing we're talking about. So you actually have a solid steel construction where you put in something that is 5 millimeters bigger than the hole. And you will see that you're exceeding 5,000 tons to press just to make the pre-stressing. So you have a conical shape of just 1 degree, and then you have more than 5,000 tons pressing those things into each other. And that gives, for one thing is the numbers and the megapascal and things, but that actually gives you an idea of how far you actually compress this inner piece of solid carbide. And it's not really solid, because in the middle there's also a inner hole, but it is this size. So you actually have a hole in a solid carbide piece, this size, 500 on the outside. Then you press on a steel ring that is 5 millimeters smaller, and then you put everything into compression. And you will see that the carbide doing so, we go so deep into compression that the carbide will have a compression state of minus 2,500, even more. So several thousands of megapascal into the minus in compression. And that is actually what helps when you start to load it from the inside.
Yeah.
Because you start in negative. And therefore you can actually load it up to the pressure shown with the 5,000 megapascal for making the synthetic diamonds.
So the first 2,500 are up to 0, and then you can take 2,500 more on the plus side.
Yes.
Or you could.
I will not go directly into the exact numbers of load.
Okay, but more or less.
But the whole basic idea is what you can go into minus. Then it's actually for free, because then it will still be in compression.
Yeah.
And the carbide is very, very strong in compression, but if you start actually to load it with tensile stresses, then it's very fragile. So therefore, you have to go as deep into compression as ever possible.
Yeah.
And you can also see the whole idea about our compression ring is actually when we have reduced the diameter of our winding core with 5 millimeters. When the standards go 5 millimeters back, it is actually back in the size when we actually bought it or manufacture it.
Yeah.
So it's actually also first starting to go into tensile stresses from that level.
Yeah. I could imagine that. I have seen some tools that broke due to fatigue.
Yes.
And you only see fatigue when you are in tensile and not in compression.
Exactly.
Is that right?
Yeah, that's exactly right. And also, if you're talking about fatigue, then I think it's actually also because we can we actually do the pre-stressing stepwise, layer by layer. Then we can actually also pre-stress carbide. Actually, the thing I have brought here, that is actually a winding core. This is actually the inner thing of a compression ring this size. So that is meant to be strip winded, and that has a complete different stiffness. And a stiffness is actually meaning if you have an inner load, then you're really reducing the strain of for every when you form a part like that. Then you actually, for every cycle, you load the die.
Yeah.
And everything expands. And this expansion is actually what driving cracks.
Yeah.
But if you then put it into a high stiffness container, then you can actually reduce this strain. And that's actually also when I started why we actually doing aluminum parts, where I said it was actually in the low pressure range.
Yeah.
It is. But still in the low pressure range, when you have complex geometry, then the dies, they will still crack because you have this going up and down. You have this strain of the die, and there you can, for the same pressure, for the same process pressure, you can actually reduce how much movement you have in your die for every cycle, and that is actually just to surround it with cemented carbide. And that you have to pre-stress. If I would put a die into something like that just in cemented carbide, it would just break immediately.
Yeah.
And therefore we put the compression ring into compression, and then we can load it with several thousand megapascals, and it's still in compression.
Yeah, that's pretty amazing. Christian, I've also seen the possibility that you could use that you can change the inner dimension, because sometimes when you press, it's difficult to get it out. But if you can relax it, then you can get it out. Is that also something you work on?
Yeah, we have, and we actually also have made application, especially for special powder compaction processes where you have springback in the materials. You can actually not deform the parts. It could be magnetic powders. There we will build high stiffness surroundings to support the whole process, but then we actually have a dynamic movement of some conical shapes that will allow us to change the level of pre-stressing, and there you will actually see that the die has a bigger diameter. We can manipulate the diameter of the die, and then we will make it smaller during forming, and then we reduce increase the diameter during deforming.
Mm.
And I'll say we have made some very successful also industrial applications, but in the low pressure area, I will call it that. If you're compacting powder, we have made it with a success. If you're going into this, I'll say, middle range cold forming application, we can make it, but when it's not stable over time, I will not call that an industrial application where you can just run it 24/7. But we actually made it for some low pressure applications and very successful, especially for making magnets. They're very hard to compact and then deform afterwards.
Mm-hmm. I know a little about that. So if we look a little ahead in the future, where are we moving? What are new potentials for strip windings?
You might have to say it's a really good question, because also we've been really had many applications in the automotive, and there we see some challenges right now. There's the whole trade conflict right now, but actually also with going into EV vehicles, there are fewer components. If the electrical vehicle, you don't have all the components in the transmission, so we have to look into the future and see what are we actually in, which way are we developing. And I can see also what we are working on is actually also doing high pressure experiments, where you can actually a little bit actually inspired also by making the diamonds that we're going into, actually also supplying equipment for making high pressure experiments, where you can actually also starting to synthesize other materials, or you can actually also start. Many of them are replicating actually what happens in the not in the core, but in the first 100 kilometers of the surface of the Earth. It's not called the core. The core is the middle. The crust.
The shell.
I think so, the crust of the Earth. Many of the actually the diamonds is made there. One example is actually when you make diamonds, you're actually replicating what happens 100 million years back, when these diamonds was actually so deep in the Earth that you had this pressure and this temperature that will actually generate the diamonds. And I could actually see that could be a way actually also of making new crystals, make new materials, and actually overcome some of these challenges we have to get around this real material shortage. Then I can see with high pressure you can actually change some of the boundaries for what you have could make it so far. And we're trying to get into that industry by supplying equipment, tooling for universities making high pressure experiments. Because actually what we're doing with the technology we're having, that is actually pushing the boundaries for what you can do. So that's actually the direction we are looking into. And actually also when we look into the net forming of parts, then actually also pursue it's actually the most effective way of making parts, as make a net shape forming of parts. And now we see vehicles going into lightweight, high strength. Then we of course also pursuing that these are the applications that will also be there for the future. But right now, actually, you actually see that the number of components in a car, they are actually massively reduced. So we have to look into these special applications where this really making a big difference, that you can make something strong and lightweight.
I have two questions left. The first might be easy. The die itself, you
Yes.
insert that in the strip winded ring.
Yes.
What happens when the die is worn out? Can you replace it, or do you have to replace everything? The winding.
It's a really good question. Actually, one of our biggest advantages actually that you can reuse the compression ring almost forever. We actually have customers. They have compression rings. They have been using them for 20 years, and
That's a bad business case for you.
Yeah, that's bad for us, but good for them. And the reason for that is actually that we could go very high with the hardness of the inner ring, and therefore we can actually allow to change many dies. So you can actually press out the die and press it in again. It's not like when you make heat shrinkage, then it's just one time use, then you have to throw everything away. Exactly. But here it's a press fit, so that will have a conical shape, and the compression ring have conical shape, and then you can press it in and out. We actually also build assembly presses for that purpose. So you can also always reuse them, also the big ones. There you will press in with several thousands of tons in and out. So you can reuse them.
Yeah. And then the last question, you said on the diamonds when they are produced, it's a combination of pressure and high temperature.
Yes.
How do you get the temperature into the die, and how do you avoid the die being heated? Because I could imagine that the winding itself, if you heat that to more than a few hundred degrees, it will not be 64 Rockwell C any longer.
Exactly. It's really good questions. But the thing is that first of all, if you have a sample inside where you actually are making the diamonds, then the part of the cell is actually also just salt, a pressure media, but it's also making insulation. So you actually have a heat shielding out to the carbide, and then you actually also have a cooling. We have different concepts of cooling. Actually, also where we have through holes into the winding core, and then we'll actually flush it with water. So you're actually starting to extract the heat so close to the cell as possible. And that is actually a balance. You're putting in the heat, and I will come back to how you put in the heat. You put in heat, and then you take out heat, and then when you have some insulation in between, then you have a temperature gradient, and the more insulation you have, the steeper the gradient, and then you can actually have 1200 degrees on the inside and 100 on the outside. It is a question of insulation and cooling capacity.
Okay.
And the heating is actually pretty simple. It is you just actually have some low voltage current running through it.
Okay, so it's just a resistive heating.
Yes, and whatever when you make diamonds, then you have a graphite already there as a conductor. And if you make some for the universities, we see they also make high temperature experiments with complete different materials. Then they will put in a graphite furnace, and that's actually a small tube. And there's actually no secret in this. You can read that in tons of papers. But that is actually, then you will put on the inside, you will put a thin tube of carbide, of graphite, and then you actually have a potential difference between it, and then you run electrical current through it, and then that will heat up, and then you make insulation on the outside, and then you actually have your sample inside this tube, and then you can actually also heat up to 2000 degrees inside that furnace, but it is made by electrical current.
Okay, so it's not a trick. It works.
No. This, but we also built actually we have built systems, also the complete tooling systems for where you actually build the container up, and then you actually have kind of a 10-ton tooling sitting there, And then you also have to take into consideration that this current is running through it. And then if you have some measuring devices or other equipment, and then you also have a couple of thousand amps running through it. Then I know our electrician, he was kind of concerned the first time we had to do this.
I could imagine.
Yeah, so you really have to see if you make some shortcuts in hydraulic hosings. A hydraulic hose is actually an electrical conductor because it is reinforced by steel.
Yeah.
And therefore you have to be very careful not to make shortcuts, because then they will just light up at a Christmas tree.
Yeah.
But that is the way it's done.
Okay, wonderful. The very last question.
Yeah.
If people want to learn more, where should they go?
I say this is a start our homepage. I will also say at actually our homepage we have also some videos where we actually make extreme loadings of compression rings. We have one just to give you an idea. If you put in a die into a compression ring, a high pre-stressing level is 10 promille, 1%. Don't say if you have 100 millimeter in diameter, you will make it 1 millimeter bigger and put it into.
Yeah.
And there we actually have some, just for the fun of it, where we are going up to exceeding 3%. And then we have also made one where we actually just keep going with the press until actually that the container is breaking. And we actually had to make the die this 200 millimeter long to reach that pre-stressing level. So that is more if you see the fun of it. But actually all what I have shown here, also some of the background, you can see a lot of it on our homepage, or otherwise they write to me. But there's a lot also background stuff on our homepage.
Perfect. Thank you very much.
Yeah, you're welcome.
I really enjoyed it, and I learned something new today.
That's good.
Yeah.
We have to learn something every day.
Yeah. Thank you.
Yeah, bye. Thank you. Good.
Bye.
Yeah, bye.